Okay, so we just learned about the chain rule. So we're going to talk about what we call implicit differentiation. So our target for today is students will find the derivative of an implicit equation by using the chain rule to find the instantaneous rate of change. Okay. So when we take the derivative of functions, we've been talking about the idea of derivatives of functions since we started derivatives. Everything we've done has been a function. But let's look at some type of functions versus equations. So if we're looking, and let me get a pen. If we're looking directly at these equations up here, these two right here, those are what we call explicitly written functions. And the reason, well, one, they're functions, of course, but explicitly that means we're solved out for our dependent variable. Y being our dependent variable in most of our functions. But we can come across equations that look like that. A lot of times we call these implicitly written equations. These are not functions, but they can be graphed. There's still a relationship between an independent and dependent variable. The difference between our left column versus our right column is our right column has an equation that can't necessarily be solved for y. Therefore, we have to treat them a little bit differently when it comes to the derivative process because we have our variables x and y mixed in our equation. Okay, so I'm going to talk about what that kind of looks like and why that chain rule is a pretty important rule for this. So if we think about taking the derivative of x with respect to x, remember this tells us right there our independent variable. Okay, it tells us the independent variable in the problem, which is important, and you'll see why in a minute, but those derivatives are really pretty easily done. Like we know the derivative of x happens to be a 1. Like we know that. Same thing with the b. We have derivative with respect to x of 3x, which we know to be just a basic 3. And then of course the last one, we know the derivative of x squared to be 2x. We've been taking those derivatives since day one. But here's the difference. This variable in our denominator of our notation of d over dx matches the variable in the problem. That means my derivative process is pretty easy. That means we really don't have what we consider to be an inside function because x on itself is not really a function. It takes a y and an x to become a function. Okay. When we think about the derivative of y with respect to x, we've been writing this as dy dx. Okay. But really the derivative of y is in fact 1, like the derivative of x is 1. But when it comes to taking the derivative of a dependent variable, that chain rule that we've learned in the last couple days starts to apply. And the reason for that is because that dependent variable is considered to be our inside function. So that we apply the idea of the chain rule to this. We start with doing exactly like we did with the chain rule, derivative of the outside. So we get 1y to the 0 times the derivative of the inside piece. We know y to be dy dx. And then if we think about that simplifying down, y to the 0 power is 1. 1 times 1 gives us 1, which is why we get a dy dx. If we look at e, that's kind of the same thing. If we think about our y as our inside function, our dependent variable, we wind up getting, again, 3y to the 0 power times the derivative of the inside, which we know to be dy dx. So it simply comes out to be a simple 3 dy dx. Now the biggest difference comes when we're dealing with something that's y squared. Well, we know the derivative of x squared is 2x, like the one above, so the derivative of y squared is 2y. But because y is our dependent variable, we consider that to be the inside piece. So we apply the chain rule anytime we're taking the derivative of a dependent variable. Okay, so right behind this, derive the outside with the inside the same times the derivative of the inside. So we simply rewrite this as 2y dy dx. The reason for that happens to deal with because of that dependent variable. If we think about it, we don't do that with x, and the reason we don't is because we would get something like this, dx over dx, which is always 1. So even though we're kind of applying the chain rule to x terms, we don't really write it like that because the derivative of the inside will always be 1. But when it comes to the dependent variable, we wind up getting something like this. And that is not equal to 1. That dy dx can change, because remember that dy dx represents the slope. And slope can change from point to point. When we're dealing with dx over dx, that's not really slope. Okay, so it just kind of simplifies down to 1. The biggest difference when we're taking derivatives of implicit functions is the use of the chain rule. Anytime we take the derivative of y, if we think about this and we think about this, the only big difference between that one and the derivative of y is that stacking on of that dy dx. Okay, so really the derivative is always going to be in addition to that dy dx. So that's because of our chain rule. Okay, so let's look at an example that we would actually do this in. Okay. Scroll down. Okay. So implicit functions are just a little bit different than our regular functions, and in fact, most of our implicit equations aren't functions to begin with. Okay, again, they're not isolated for y. We have x's and y's on both sides of the equation, and so we take the derivative a little bit differently with the use of the chain rule. So for instance, the first example on here says to find the slopes of the tangent lines to points 3, 4, and 3, -4 on the graph of the circle defined implicitly as x squared plus y squared equals 25. So that equation, if we graph it, represents the circle that we see right here. So we're going to concentrate on finding the derivative at that point and finding the derivative at that point. Okay. But first, if I want to find the slope, because that's what we're going to find, the slope of that tangent line that we see drawn in there. Let me get a different color. Let's not get purple since it's in purple. So that line right there, we're going to find the slope of that tangent line and the slope of that tangent line, because we know our tangent line and our equation or our graph have the same slope at that point of tangency. We've talked about that before. Okay, so if I wanted to find the slope, find the derivative, I would have to use what we call that implicit differentiation. What's going to change is we're going to actually wind up taking the derivative of everything from left to right. Every single term is going to involve a derivative of that term. So for instance, if I take the derivative of that x squared, we know that to be 2x. That's not different because x is in fact the independent variable here. Then we go plus, and then when we take the derivative of the dependent variable, we will wind up getting a 2y times the derivative of the inside. And the derivative of the inside of a dependent variable is always going to be that d whatever over dx in this case. And of course equals, and then the derivative of 25 is going to be 0. If you're going to make a mistake in this process, not taking the derivative of every term is where you're going to make a mistake. So for instance, if I didn't take the derivative of 25 and just left it as 25, that's a big mistake because we want to take the derivative of every term in the problem, no matter what side of the equal sign they're on. After this, we know that the true derivative, the true slope, is that dy dx. So what we do from here is we just solve out for that highlighted term. So first thing I'm going to do, of course, is subtract 2x from both sides. And I get 2y dy dx equals negative 2x. And if I'm trying to isolate the dy dx, I'm going to divide both sides by 2y. So we wind up getting dy dx equals, and if I simplify that down, I get negative x over y. So there's our slope equation. If we're starting with an implicit equation, an equation that has x and y's mixed, more than likely our derivative is also going to be implicit, x and y values mixed. Okay, so we want to see the slope specifically at those 2 points that I said at the beginning, so we're just going to plug them in. So we're going to take our dy dx and evaluate it. Now often we put x equals the number, but we have an x and a y, so we're going to write at the bottom of that the actual point that we're going to plug in. So we're going to evaluate the dy dx at the point 3, 4. All I'm doing is plugging in 3 for x, 4 for y, and we get our slope. Now if we think about that point, that's that line right there, has a negative slope, so it makes sense that our derivative is also negative at that point. I want to do the same thing. I'm going to evaluate dy dx also at 3, negative 4. So I'm plugging in a positive 3 for our x and the y value for our y. If we simplify that down, we get a basic 3/4. And that right there is that line. Okay, obviously positive slope, positive tangent line, so it kind of matches up to it. So only big difference in taking the derivative of these is right behind any time you take the derivative of y is going to come a dy dx through multiplication. And that again is because of our chain rule. Let's go on to the next page. Okay, we want to just find the derivative of these equations. Okay. So I'm going to start taking the derivative left to right. Anytime I take the derivative of y, right behind it is a dy dx. So derivative of y squared gives us 2y, right behind it a dy dx. That term's done, plus derivative of 2y gives us 2, right behind it a dy dx. Minus derivative of 3x to the 4th gives us 12x cubed, and then equals derivative of 4x gives us 4. Okay, after that, all we're really doing is solving for dy dx, just like we would solve any algebraic equation. I want everything that has a dy dx on one side, everything else on the other side. So the first thing I'm going to do is just add that 12x cubed, and I'm going to add it to both sides. So I get 2y dy dx plus 2 dy dx equals, I'm going to put the 12x cubed in front, plus 4. Okay, the whole point of this is to solve for dy dx, because that is the true slope equation. So one of the things I could do at this point in my problem is I could factor out the dy dx. And I wind up getting 2y plus 2 equals 12x cubed plus 4. Okay, and then because I'm solving for the dy dx, I'm going to divide everything by that 2y plus 2. And that means I get dy dx equals 12x cubed plus 4 over 2y plus 2. Now, if I wanted to simplify this, I could only simplify it through factoring. So if I can factor out something from both numerator and denominator and it's the same thing, then I can cancel it out. In this case, I can factor out a 2 across the board. I get 6x cubed plus 2. I could factor out more, but I'm only going to factor out what I need to cancel out. And I get that. Okay. once I do that, my 2's will cancel out, and I'll wind up with just basic 6x cubed plus 2 over y plus 1. And there's my derivative, my slope equation, again in terms of x and y. Now for the next example, if we look at it and we read it, this says x squared minus or times y equals 3x. So the one thing we have to remember, all the rules that we've learned, product, quotient, chain, all those rules still apply because we are doing a derivative. So if we look at that term right there, we have some multiplication going on, which means if I want to take the derivative of that, I'm going to need my product rule. Okay, so I'm going to use product rule to take the derivative of the left side of that equation. So the product rule says take the derivative of the first times the second plus derivative of the second. Derivative of y gives us 1, right behind it, dy dx times the first equals, and then of course the derivative of 3x is just a simple 3. Okay. So after this, I'm just going to subtract out 2xy from both sides. I'm going to multiply that 1 and the x squared, so I get x squared dy dx equals negative 2xy plus 3. If you wanted to write it 3 minus 2xy, that would be fine as well. And then last step is to, of course, divide out what's with the dy. So I wind up getting dy dx equals negative 2xy plus 3 over x squared. Nothing really to factor out, therefore there's nothing to cancel out, so I'm done. Okay, so really when we're taking the derivative of an implicit function using implicit differentiation, what we're really doing is 4 basic steps. We're differentiating both sides of the equation with respect to x, or the independent variable. Okay. We're collecting the terms of dy, anything that has a dy dx, we're going to collect it to one side. If there's more than one dy dx, we're going to factor out the dy dx, and then of course just solve. And often solving is through division. Okay. So what I want you to do is I want you to try this problem on your own. So go ahead and pause the video, try it, and then replay to see if you got the answer. Okay, so if you did the derivative right, this is the equation for that derivative. Okay, again, for that term right there, I used product rule. Okay, and that's what, if you look, that's what's right here. That's the result of the product rule. And then, of course, the rest of the equation right there. Okay. This has a dy dx on both sides, so I'm just going to move it over. I'm going to move this one over to that side. So I'll get 2xy minus 3 equals 3y squared dy dx minus, I'm going to just put the x squared in front. Okay, I get that. Okay. Factoring out, not 3. I don't know where the 3 came from. I get that factoring out, which means my dy dx is equal to 2xy minus 3 over 3y squared minus x squared. So there's my derivative part. So we're trying to find the equation of the tangent line in this problem. We have the point, the x and the y, so we really didn't need to do that. Okay, we took the derivative, and now we're ready to actually plug in to the derivative. I'm going to use a different color just to show my steps. So we're going to take our dy dx. We're going to evaluate it at -1, 2. So everywhere there's an x, I'm putting in -1. Anywhere there's a y, I'm putting in 2. 3, 2 squared minus -1 squared. And we're just going to calculate what this is. So we get -4 minus 3 on top. We get 12 minus 1 on bottom. So -7 over 11, like the convenience store. Okay. And then our last thing to do is to write the equation of the tangent line. So y equals my y value, so remember I'm using this point, y value plus our slope times x minus my x value. And then I'm just going to clean this up because I do not like double signs. So we're just going to clean it up. And there's the equation of our tangent line. Okay, so we're going to stop here. The last two examples we'll do in class. They are a little bit more complicated, so I want to actually talk about them with you guys in the classroom. So if you have any questions, come and see me.